All right, in this video, we're going to cover section 4.2 of chapter 4, and that's about calculating sampling distributions. And it turns out we've already sort of seen a few of the ways that we're going to do this. So section 4.2, we won't be covering a lot of new ground. All right, so in general, there's three methods to calculating a sampling distribution and things like its mean or its standard error, right? First, we could try to calculate it exactly. So there's two ways of doing that. If we first, so remember with the sampling distribution, a test statistic has to be to us. I want the sampling distribution of sample mean if you grab 12 values or the maximum of 12, right? So we have to be told a test statistic and we create sampling distribution of that test statistic, okay? So to do it exactly, we might first have to compute all possible random samples and then calculate the standard error or the histograph for the distribution, okay? Now, if you're going to calculate all possible random samples with which you would use to generate the values of your test statistic, it requires that we must know the entire population. Okay, and we did in a very small case in video B, we had the 4-value population. All right, but if you don't know the population, you can't hope to get an exact calculation by looking at all possible random samples, right? The other way we could find the exact sampling distribution and its standard error and its mean is to use formulas specific to the distribution. So, for example, in exercise 4.2, I believe we were told we're going to sample from an exponential distribution with lambda equals 1/15, right? So we were told the distribution, all right? And then we got the exact standard error of the sampling distribution for the test statistic, the sample mean of whatever it was, 10 random values, okay? But in this case, again, we have to know or must know the distribution. All right, and I'm emphasizing this because for a lot of the rest of the course, we're not going to know the distribution or we're not going to know the entire population. We're just going to be given one pile of data that's part of the population and comes from some distribution that we don't know. So we're not going to be able to do method 1 exact calculation too often in the rest of the course. But we've seen examples of both of those. The second method is to do simulation, which we've also seen examples of, and that's to use R. So maybe we run 5,000 or 10,000 or 100,000 random samples and approximate the sample distribution and its, and its mean and standard error, okay? So we did this when we looked at the tossing a fair coin 10 times and recording the proportion of heads that we see in one of these 10 toss trials. We did that, I think it was 5,000 times and approximated the sampling distribution and the standard error, okay? All right, and then the third method is we can perhaps approximate these formulas from 1B via the central limit theorem. And that's going to be the focus of section 4.3, so I won't talk more about that until then. All right, so the rest of section 4.2 is just a specific instance of where we can do an exact formula approach. So please pause, copy down, and then press play. And it's likely that you've seen this result from Math 313, all right? And perhaps we'll prove it in class, or at least one of these two in class. All right, so here's another time we can get an exact value for the sampling distribution, the standard error or some such thing. All right, so suppose we have independent and identically distributed random variables, x1, x2, up to xn, from a distribution whose PDF and CDF I know or have been given to me, all right? Then for two test statistics, I can calculate the PDF perfectly. The first test statistic would be select the minimum of those n random variables. That's going to be our test statistic. In which case, the PDF of that test statistic, f sub min, is n times 1 minus capital F to the n minus 1 times lowercase f, right? So that's the PDF of the minimum value of n random variables from that distribution. Similarly, the second test statistic could be to select the maximum of those x values. So the max of x1 through xn. And its PDF is f sub max, and it would be n times capital F to the n minus 1 times lowercase f. And that should stir some love and joy from your Calc 1 side of your brain. That sure does look like the chain rule. N, F, n minus 1, f prime. And that'll be part of the proof. Okay. All right. So you should know those two, like by the time we have an exam. All right. So let's take that formula out for a spin. Okay. And maybe I'll move it a bit closer. All right. So pause, copy, play. All right. So in this example, I have x1 up to x12 are independent and identically distributed IID random variables from a distribution whose PDF and support is provided. Don't even need to say support. The PDF better include which x values it intends to be over. Otherwise, you don't have a PDF. You just got a function. All right. All right. And we would like to know two things. I'd like to determine the PDF of the sample statistic x min. And it's not very clear. Is it x min? And determine the probability that x min is less than or equal to 1.3. Okay. All right. So solution in 3 steps. First off, from the previous panel, to get the PDF of x min, I need the CDF of the original distribution. I need capital F. So that's going to be step 1. Determine capital F, the CDF of the distribution. By definition, the CDF is the area from the start of the distribution up until x of the PDF. All right. And notice with the PDF, I've replaced x with t because x is now my upper bound. All right. So I'm going to integrate 2 over t cubed. That's 2 times t to the negative 3. So t to the negative 3's antiderivative is t to the negative 2 over negative 2. The 2's cancel, so I get a negative sign and a t to the negative 2. Integrated from 1 to x, so plug in x, plug in 1, simplify, same support. So there's the CDF of the original distribution. Step 2, I can now grab the PDF of x min. I have a formula for it. My n is 12, so there's my n, 1 minus capital F to the 11th times lowercase f. So I can replace capital F with 1 minus 1 over x squared and lowercase f with 2 over x cubed, what we were given and what we determined in step 1. 1's cancel, the negative sign cancels. 1 over x squared to the 11th is 1 over x to the 22nd. And then 12 times 2 is a 24, x to the 22nd, x cubed is x to the 25th. Same old support, x greater than 1. So there is the PDF of my test statistic, x min, and it's 24 over x to the 25th. Okay. Not sample statistic. Come on, Excel. Get a grip. Test. Okay, well, there it is. And then the second part of the question is, what's the probability that this new random variable x min is less than or equal to 1.3? Well, I've got its PDF, so I could integrate its PDF between 1 and 1.3. So back to Calc 1, x to the negative 25th would become x to the negative 24 over negative 24. 24's cancel, so I get negative 1 over x to the 24th from 1 to 1.3. Plug, chug, and I get 0.9982. So there's a formulaic way of getting the exact PDF of the test statistic. And if I wish to calculate the standard deviation of this test statistic, I could simply calculate the variance of x min using, that variance formula, e of x squared minus e of x quantity squared, and then take the square root to get the standard deviation. Okay,